Looks like we've got a fair number of people who have joined, and we'll probably have some more coming in. First off, I just want to welcome everyone to our first Young Scholar webinar on climate finance and economics. This is a project that we are very excited about to be working with eAccess doing and putting together a venue and a place for young scholars to be able to present their research in this area of climate finance and climate economics that we think is very important and very exciting. And there's just a lot of great research. So we're really excited to be able to do this and have this opportunity. I'm Mike Barnett. I'll be moderating today. I'm an assistant professor at Arizona State University. And my colleagues that'll be helping co-organizing this, I'll just introduce them real quick as well. They'll be joining us and moderating our other webinars. It's Diego Kenzig at Northwestern, Elisa Kleinenhaus, who's at Imperial, and Ashita Sen from HBS. So first, I want to thank them for all the work they've put in with me to try and get this organized. And for those at eAccess, Anastasia, who's been helping us make this happen. Apart from that, I will introduce our speaker, and then we'll get started from there. So we are super excited that we have Tuomas as our first presenter in the webinar series. He's an assistant professor at Boston College. His primary research is focusing on asset pricing, financial intermediation, insurance market, and climate finance. And he's currently working on understanding the role of financial markets and mitigating the effects of climate change on the society. He has his PhD from Columbia, and he's just a great researcher. I've really enjoyed reading his work, and we're super happy he's our first presenter. So, just in terms of timing as well, we are going to have a poll at the beginning where people can answer a couple of questions that will help spur the discussion. Thomas said he's more than happy to answer some clarifying questions and that come up during his presentation. And then as we have time towards the end, we will answer as many questions as we can get to. Feel free to go ahead and put those in the Q&A, and we'll try and get, if we can, have you ask those directly yourselves, or we'll read them off the Q&A for you as we go along and at the end. So without anything else, I think we'll turn the time over to you, Tuomas.
Great, thanks, Mike. Thank you so much for inviting me here today. Let's see, Anushka, could you stop sharing your screen so I can share mine? Can you see this?
Yep, looks great.
Okay, very good. So today's paper is joint work with Viral Acharya, Tim Johnson, and Suresh Sundaresan. In this paper, we asked the question of whether physical climate risk is priced in financial markets, with a specific focus on projected increase in extreme temperatures or heat waves. So first things first, why should we be interested in understanding whether exposure to heat waves is affecting prices or not? Well, when climate change damages are being discussed, especially in the popular media, attention is oftentimes given on some of the more disaster type consequences of climate change, things like hurricanes and sea level rise. But actually, according to many projections done by climate economists, these type of hazards, climate hazards, are actually expected to cause relatively small damages to the US economy as a whole. So here's a graph that shows you one set of projections for different types of risks. And what turns out is that vast majority of damages, at least here in the US, are expected to be directly related to extreme temperatures. So these type of effects, they typically are a little bit more subtle in nature, but when ambient temperatures are very high, many bad and economically costly things tend to happen. So of course, energy demand increases, but at the same time, electricity supply contracts because energy production and transmission are less efficient during hot ambient temperatures. Also, things like labor productivity is negatively affected. This is especially true in so-called high-risk industries where workers are directly exposed to outside temperatures. Think of industries like construction or mining or agriculture. But to some extent, this is true for other industries as well. So with the big caveat that this type of bottom-up projections of climate damages, they are extremely sensitive to underlying assumptions about things like adaptation and general equilibrium effects. The point still stands that quantitatively speaking, heat waves stands out as the most important channel through which we expect climate change to cause damages to the US economy. So despite the importance of this climate hazard, relatively little is known how it's actually affecting things like forward-looking asset prices. And this is what we study in this paper. So we study 3 different asset classes, municipal bonds, corporate bonds, and equities. For each issuer, we have a measure how exposed they are to projected increase in extreme temperatures. And across these 3 different asset classes, we find consistent evidence. So for muni bonds and corporate bonds, higher exposure is associated with higher credit spreads. And for equities, higher exposure is associated with higher conditional expected return on equity. So what this last result implies is that there's risk premium, discount rates are being affected. We also study the cash flow effects. Essentially, we use the expected default frequency, or EDF, from Moody's KMB as our measure for physical default probability for corporations. And we find that this is also positively associated with the exposure to heat stress. So we find evidence both that the cash flows and the discount rates are affected. We don't try to formally decompose the total effect into these 2, but we still find evidence consistent with both. Finally, we have similar exposure measures to other climate hazards that are out there. We don't find systematic evidence for these other risks. This doesn't mean that such effect does not exist. In fact, there is a rich literature that precedes us that have focused much more closely and clearly on these other hazards and have found consistent evidence with positive price impact. But the way we interpret this is that because our sample consists of a very broad cross-section of test assets, we don't try to target any particular hazards in terms of trying to maximize the variation in exposure to any particular hazard. The way we interpret this is that it's also plausible that we just don't have enough power in our broad sample to pick up these other effects. And what it means is that it seems that market prices on aggregate do seem to agree with this climate economist projections on the importance of heat waves, in particular when it comes to the effect of physical climate risks on asset prices on aggregate. So here is our main results for muni bonds. Essentially, we estimate year by year how heat stress exposure is associated with muni bond spreads. Early part of our sample, we don't really find any difference between high and low exposure issuers, but towards the second part of our sample, a gap starts to emerge so that higher exposure issuers, the bonds that they issue have a little bit higher credit spreads compared to less exposed issuers. Here is the same results for corporate bonds and equities. Again, similar pattern, little evidence in the early sample, which then increases towards the second part of our sample. And this type of pattern is very much consistent with some of the earlier literature that I mentioned. How do you explain a pattern like this? We don't try to formally test what is the reason, what caused this difference in spreads to emerge. But if you just superimpose something like a time series graph from Google Trends that shows you how much people have been using the search words climate change in Google, kind of like a measure of how much attention, how concerned people have been about climate change, you see that the increase in attention has started to increase around the same time when we see this spread to emerge. It could be due to many different reasons. So we're not trying to answer that question here, but overall, it's the time series pattern is very consistent with the timing on when people started to be more concerned about this phenomenon. Let me skip the literature in the interest of time. There is a lot of good work that has been, of course, done. But let me go directly into our the rest of the paper. So what I'm going to do is I'm first going to go a little bit more in detail. How do we measure heat stress exposure? And then I'm going to go through our results asset class by asset class before providing some interpretation and concluding remarks. So we use two complementary sets of measures in our paper. The first measure builds on the work of Solomon Zhang and co-authors. In their 2017 science paper, they developed something called Spatial Empirical Adaptive Global to Local Assessment System, or SEAGLAS for short, to estimate economic damages from climate change in the US at county level for various different climate hazards. And the output of this model is essentially an estimate that compares the projected annual economic damages under the so-called RCP 8.5 climate scenario to a baseline scenario where no further climate change takes place during the century. Now, this RCP 8.5, it's sometimes called the business as usual climate scenario. I think the name is a little bit misleading in a sense that it's a relatively severe scenario that we would expect to occur if we basically completely fail to curb carbon emissions over the next decades. So you can think of this measure as being kind of like a stress test measure at what would happen under a relatively severe scenario compared to a counterfactual where nothing would happen at all. So SEAGLAS is being used to assess various different types of climate change consequences. The ones that we are going to be focusing on are economic damages that are directly associated with extreme heat. So we'll look at the effect on energy expenditures and labor productivity. So to construct these types of estimates, there are several different steps. We follow Zhang et al. And the first step is to construct these type of probabilistic projections on daily temperature distributions. We will be using the output from 44 existing climate change models, and we basically take the average prediction across these 44 models. And the output of these models is here illustrated for Orlando and Miami. They essentially show the annual temperature distributions, the maximum temperature, how many days the maximum temperature is going to be in a particular threshold or in a particular bucket. So the blue distribution shows you the baseline distribution for Orlando, for example, on your left. And then the red distribution shows you how the annual temperature will look like in Orlando under the RCP 8.5. And our simplest kind of like do-it-yourself exposure measure, which we call delta projected hot days, is simply the projected change in the number of days that the county spends over 100 degrees Fahrenheit between RCP 8.5 and the baseline scenario. Now, if you compare Orlando and Miami, you can see that Orlando is much more affected by climate change. Across all counties in the US, Orlando is in the 76th percentile of all counties. Miami is much less affected. It's only in the 24th percentile among all counties. Now, as I mentioned, we could use this as our measure and the results would go through. But in order to get a little bit better sense on quantities, what Zhang and co-authors do is that they convert these changes in temperature distributions into predicted economic damages using hazard-specific dose response functions. So for example, to estimate impact on energy expenditures, They used a model called National Energy Modeling System by US Energy Information Administration that is being used to model the supply and demand for the electricity grid for the US as whole. It's kind of like an engineering model. And if you now shock that model with different temperature assumptions, that model will tell you how the supply and demand will react to that type of a shock. For labor productivity, they use estimates from a paper by Graf, Siffin, and Neidl. That it's a well-cited paper in labor economics that studies how outside temperatures affect labor productivity. And basically, as an output of this type of transformation, you get kind of like a scale-free percentage measure of how things like energy expenditures and labor supply change as a consequence of climate change as we move from the baseline scenario to RCP 8.5. The last thing we do is that we convert these percentage estimates into dollar damages using data on 2019 data on things like energy prices and wages and local GDPs. So ultimately, we will get like a measure of what the damages will be as a percentage of local GDP, assuming that the economy will be similar in the future as it is in 2019. So then we have a second measure. It comes from a company called 427. That's a subsidiary of Moody's. They have done similar exposure assessment across the globe for various different climate hazards, including heat stress. And this is essentially kind of like a fully relative measure. It's a score between 0 and 100. 100 means very exposed, 0 means little exposure. The one benefit of 427's approach is that because they have done this globally, SEAGLAS is only for the US, and they have data on the location of physical assets of corporations. Think of things like offices and production plants. They can actually use that plant level data to aggregate this exposure measure to the company level. So that's a big benefit of their approach. The downsides, of course, it's a proprietary black box model. We cannot really go into the details of how it works. We can only compare the output to SEAGLAS. They look quite similar, but we cannot really go into those details. Second downside is of course that it's a fully relative measure. It's a score. It doesn't give you any sense of a magnitude. So here is how our summary statistics look like for these measures in the cross section of US counties. The first row, energy damage. This is our SEAGLAS measure. The average value is 83 basis points, which means that the average municipality in the US is expected to lose 83% of their GDP as a direct consequence of climate change. You can see that the minimum value for this measure is actually negative. Some of the municipalities are actually expected to benefit from climate change due to the net effect of milder winters being bigger than the negative effect of hotter summers. But for the average municipality, the net effect is still positive, meaning that the average municipality is expected to suffer from this hazard. Another thing I want to point out, the median value for this delta projected hot days is 37, which means that the number of extremely hot days for the median municipality in the US is expected to increase by 37 days per year from the baseline value of 0.4. So at the moment, the median municipality is on average experiences 1 day every 2 years under this type of extreme heat wave conditions. That is going to be increase all the way to more than 1 month every single year under these extreme conditions. So the effect really is a very, very big for the average municipality. So let me see, there is let me actually, before I go forward, let me make one more point, which is that, as I mentioned in the beginning of the presentation, these types of climate damage projections. They are very sensitive to things like what do you model, what do you assume about things like adaptation. So in the paper we have a whole section discussing what type of factors may cause us to overestimate versus underestimate these damages. And there is a lot of modeling uncertainty that definitely goes into an exercise like this. One thing I do want to mention is that our results are not sensitive to any of these underlying assumptions, even if we don't do these transformations from temperature shifts into economic damages, the results still go through. So basically, the only thing we need is that kind of like the relative ranking stays intact if you would adjust for multiple different things. Those municipalities that are most exposed under our measure would also be most exposed under the more accurate measure, if you will. And as long as that ranking is preserved, the results go through. We will estimate the magnitudes wrong, but the direction stays the same. So then there's a question about, given the forecasted temperature rise, are the expected economic damages correlated with the past one in the cross-section of US counties? That's a good question, and it's a little bit hard to say because as you see from this increase, in the past we haven't really seen this type of extreme hot events that we are expected to see in the future. So projecting from past data in the future when it comes to climate change, it's not really going to work as well as it works for many other economic phenomena, simply because we don't have data on the types of states of the world that we expect to see in the future. And that's why you need to rely much more heavily on these types of projections that are built on like first principle underlying assumptions rather than necessarily on the past data, simply because the future data that we of course don't observe today is expected to look very, very different than what we see in the past. But definitely there is evidence for things like heat waves having less of an impact in hot regions, simply because there are more AC units out there. They're already better adapted to this type of things. So due to these type of things, you would definitely expect that hot regions are better able to adjust in the future than the cold ones to mitigate some of the differences. Okay, so before I go into our results, let me talk about one important empirical point before that. So here on the left, you see a map of the US that shows which areas are most exposed to heat stress under the 427 measure. And yes, heat wave exposure does change across the country, but so do many other things. Local economic conditions are very different in some parts of the country than in others. So a natural concern that arises that perhaps our measure is just correlated with some underlying differences in local conditions, the creditworthiness of the issuers, and that's what we are picking up with our measure, which has nothing to do with climate change. So this is a standard concern in the climate finance literature. The way that previous studies have typically tackled this is that they rely on geographic discontinuities. So for example, if you study the effect of sea level rise on the prices of coastal assets, one thing you could do is that you could take an issuer that is located at the coastline and compare that issuer to its neighbor who is located just a little bit inland, and assume that the local economic conditions are similar across these neighboring locations. Which then allows you to control for these local conditions and tease out the effect of physical climate risk. In our case, this type of strategy is unfortunately not feasible, which is pretty clear if you compare these two different maps. And the reason for this is that heat by its very nature wants to distribute itself as evenly as possible. We don't really have this type of big exposure gradients when it comes to nearby geographic location. So we cannot really rely on this type of approach that previous literature has used. So instead, what we will do is going to build on the following observation, which is that historically speaking, credit ratings have not reflected physical climate risks. And this is perhaps stated most explicitly in 2015 white paper by Moody's, where they discuss how environmental risk affect their credit rating assessments. They say that based on the current limited visibility on the nature of climate change, direct climate change hazards are not at present a material driver for ratings. All these different companies, they have updated their criteria over the past few years, 2021, 2022. So for example, S&P in its 2021 ESG risk rating framework, S&P actually states that among all different types of ESG related risks, they expect physical climate risk to be the most material driver for creditworthiness in the future. That said, in order for these type of risks to affect credit ratings, S&P also requires that there is quote unquote sufficient visibility and uncertainty about these types of impacts. And generally speaking, physical climate risks don't meet these criteria because the envelope of uncertainty and the modeling risk when it comes to how big these damages are and when they do occur is too big for these type of damages to be feasibly being implemented into kind of this type of a deep dive credit rating analysis that these companies specialize in. And I've actually gave this presentation in S&P Global Methodologies Forum, talk with some of the lead authors on this ESG rating criteria. They were very helpful helping me to understand this better and clarify some of the finer details. But overall, they definitely agreed with our read on their white papers, which is that it would be nice to take this type of risk into account, but currently it's simply not feasible because there is too much uncertainty about what's gonna happen about these risks. So why does this matter? Well, it matters because this observation allows us to include very flexible year times credit rating fixed effects into our specification to control for any type of traditional risk factors that affect the creditworthiness of the issuer that the credit rating models are meant to capture. Now, normally, if you have some kind of variable that you think affects creditworthiness, you cannot really include credit ratings into your specification as a control, because any type of factor you think has an impact on creditworthiness should also have an impact on credit ratings themselves. So including credit ratings as control would introduce a bad control problem, making your coefficient estimates very difficult to interpret. But because in our case, we know that these models have not built to account for this type of risk, we can include them and kind of level out other types of credit risk factors that credit rating risk models are meant to capture at a very detailed at issuer level. We can kind of control for them with this approach. So basically, the underlying assumption then becomes that that credit ratings do a good job of capturing other type of risk. So the assumption really is that there isn't any other omitted risk factors from the credit rating models that are as important as physical climate risk that have increased over our sample period, and that would be correlated with heat stress. We do add a bunch of controls into our specification on top of these risk factors, just to rule some alternative stories out. But it's very robust to any of these types of inclusions. So in the interest of time, let me skip the details of the sample itself. When it comes to municipal bonds, our sample is very standard. We include most of the bonds in the muni bond universe in the sample. The key thing that we exclude is bonds issued by state governments, because these type of bonds, their geographical footprint is the whole state instead of just one municipality or county. Because of this type of big footprint, it's very difficult to assess how exposed they are to this type of risk. So the state issued bonds are not part of our sample, but all the local ones are, as long as they meet these other criteria that are very standard to the literature. Let me also skip the summary statistic and go straight into our specification. So basically what we do is we run a specification that is very similar in its form to a dynamic diff and diff specification. Basically, we estimate for each year how much increase in heat stress exposure affects credit spreads after including these fixed effects that I mentioned, plus some other standard control variables. Here is how our results look like for muni bonds. The first two columns are for the SEAGLAS measure. The last two columns are for the 427 measure. If we compare the third and fourth column, for example, the only difference between these two is that the fourth column includes this rating times year fixed effect. The third column does not. As you can see, that doesn't have all that big of an impact on our estimates. These estimates suggest that towards the second part of our sample, higher exposure to heat stress risk is associated with higher credit spreads. So for example, 2019 estimate would be something like 8 basis points for each standard deviation of risk exposure. And again, the fact that the credit ratings don't really have a meaningful impact on our results suggests that no standard factors affecting credit risk is really driving our results. We repeat this analysis for various different subsamples. We find that the result mainly comes from bonds with low credit rating, lower credit ratings instead of very high quality bonds. We also find that the result mainly comes from long dated bonds with plus 10 years plus time to maturity. And it comes from the subsample of revenue bonds, where the cash flows or the cash flows that are used to service that debt are directly related to some kind of one particular project instead of the whole balance sheet of the municipality, for example, exactly the type of projects you would expect to be more exposed to this type of risk. Okay, so after looking at the municipal bonds, we turn our attention to corporations. The main difference between these two is that for corporations, we don't have the SEAGLAS measure available because it's only estimated in the US. So we'll be relying on the 427 measure. Again, data very standard when it comes to the universe of corporate bonds. The specification we run is again very similar that we had for the mini bonds. The control variables are a little bit different, but we again control for credit rating fixed effects times year. The results look very similar. Again, we find higher exposure means higher credit spreads during the second part of our sample, but it actually only concentrates on the subsample of bonds that are junk bonds, non-investment grade bonds. We don't really find similar evidence in the full sample or for the highly rated investment grade bonds that, even if they do experience some losses due to climate change, that doesn't necessarily push them all the way that much closer to the default boundary. So as long as they are well capitalized enough, they probably have enough profitability or capital buffers to eat this type of shock. And again, you would expect that companies that are already more financially distressed would be the ones that are more affected by this type of extra losses. The next thing we do is we change the Y variable. So we instead of looking at spreads, we study how heat risk exposure is associated with expected default frequencies. So this EDF, expected default frequency, it's constructed by Moody's KMV. Basically, it's a measure that reflects the mapping from Merton model implied distance to default into physical probability of default for the firm. So based on the market price of the company, we can create a measure of how close this company is to default threshold. And then based on how close you are and based on the historical default frequencies of companies in these different types of buckets, Moody's estimate how likely it is for the company to default based on historical default frequencies and forward-looking market prices that we see today. So using this measure, we again find that higher exposure is associated with higher cumulative default probability. It's something like 30 basis points cumulatively over the next 10 years. Mainly again much bigger for the low rated bonds. The final thing we do is that we look into equities, and the reason for that is that if you look at credit spreads, that is basically affected. The reason why heat stress exposure might be affecting credit spreads, there are two different components that go into that. The other is that if there is indeed a higher default probability, investors demand actuarial compensation for these higher expected losses, which doesn't yet tell you anything about whether there is any type of risk premium attached to that type of a risk. And the reason why this is interesting is that different theoretical models of climate change would actually predict different signs for this risk premium. Some of the models predict a positive premium, other models predict negative. But because this expected loss component typically is so much bigger, it's going to dwarf any risk premium estimates. You cannot really observe that from just looking at credit spreads. And to try to make a little bit more progress in this type of decomposition, we turn our attention into equities, where expected returns have been traditionally been measured. So the standard way to measure expected return on equity is to look at historical data and look at the average historical return, a realized return, and use that as a measure for expected return. In our case, this would be a very difficult thing to do due to the time varying nature of climate change. So there are recent papers, Pastor Stambaugh Taylor, for example, that argue that over the past 10 to 20 years, there have been permanent shocks when it comes to things like people's preferences towards green versus brown, attention to climate change and things like that. Also, our estimates of the probable pathways in the future when it comes to how severe the climate change is expected to be have become worse over time to some extent. So basically, in this type of very non-stationary environment, there is not a good reason to believe that historical average returns would actually converge into forward-looking expected returns. And for that reason, we need some kind of a conditional measure for expected return in order to make progress. What we will do is that we take advantage of some of the recent advancements in terms of measuring expected return in the asset pricing literature. So Martin and Wagner, in their 2019 JF paper, they suggest that you can measure conditional expected returns from the options data, where it's going to be related to the risk neutral variance of the underlying stocks compared to other stocks that are out there. So this is something that quite a few researchers have applied recently in their work. The one thing that kind of made me convinced that this seems to be a good measure to capture cross-sectional variation in expected returns is that if you take this is a graph that comes from their paper directly. If you take the average prediction that you get from their measure for expected return and map that against the average realized return, you see that these two line up very, very nicely. So at least on average, their measure seems to be doing a very good job of capturing variation in expected returns. So that's why we're going to proceed with this one. So well, we are going to be running very similar specification that we did for the bonds. The only main difference is that now we only have one observation for firm, the price of the stock instead of multiple different bonds that may be issued by the same issuer. Also, credit ratings here don't really make sense anymore. So this is not identified in a sense that the previous results were. But if you compare how this measure of conditional expected return is associated with the expected returns, you again see the same pattern arising that during the second part of our sample, higher heat stress exposure is associated with higher conditional expected returns on equities. So what does this mean? As I mentioned earlier, increasing climate change risk exposure should unambiguously decrease the asset price, but the sign of the risk premium is ambiguous. Under some models, climate change risk acts as a hedge against macroeconomic shocks. So the idea is that if the macroeconomy is doing well, there is going to be a lot of pollution, which means that the climate change is going to materialize in a bad state, but at least the economy is doing well, aggregate consumption is high. So climate change actually hedges you against macroeconomic shocks. For that reason, the risk premium on climate risk is actually going to be negative. Under some other models, climate change directly decreases aggregate output. Bad climate state is also bad macroeconomic state under which the premium would be positive. And the previous result that we just had is more consistent with the second class of models where the climate risk premium is positive. I'm going to skip this other risk and go directly to conclusion. So basically what we show is that heat stress seems to be a systematically priced source of risk across different asset classes. The fact that we find positive risk premiums is again more consistent with the second class of models, where climate change itself is expected to cause direct damages to the economy to the extent that the economy is doing bad when climate change is very high. This has very important implications for climate abatement because it implies that any type of a project that is being used to mitigate the effects of climate change, you should apply very low discount rate to these type of projects, actually something that is below risk-free rate, which makes more of them NPV positive and worth taking. Anything that can prevent climate change is according to these estimates worth investing in because of low discount rates, even if you get some decent benefits out of it. Second conclusion, how you measure physical climate risk exposure is important. One way you can think of our paper is that we ask kind of like a second opinion from the markets. What do you think is an important source of physical climate risk? The estimates seem to agree with the climate scientist projections that if you want to measure physical climate risk, what is important, it seems that heat stress is definitely an important component when it comes to trying to, if you want to protect yourself against climate risk, if you want to hedge it, for example, heat stress is going to be the most quantitatively important component of that. So with this, I would like to thank you all for your time and attention, and I would be very happy to take any questions you might have.
Great, thanks so much, Tuomas. Just a reminder, so we already have a few questions in the Q&A, which we'll sort of go through. But anyone who has any questions, feel free to type them in the Q&A in the chat, and we've got about 15 minutes or so for some Q&A. So maybe I'll just start going through some of these, Tuomas, and you can answer some of them. First one was sort of the most recent question. This was a clarifying question, might be useful. So it said, can you please clarify which heat score you're implying is your dependent variable? In particular, they're saying that I see no time dependency. Yes, that's a good catch. So the scores that we are going to be using for 427, we used the 2019 snapshot that they give us. We also have a few other vintages that the correlation across years is almost exactly one when it comes to rank correlations. So that is one of the limitations that we have, that we don't observe if the relative ranking of risk exposure changes year by year. We are essentially assuming that the ranking stays the same year by year. The reason why we think this is reasonable is, first of all, because we do have a few different vintages. The results, the variables are very, very similar.
The other reason is that the 427 measure is from 2019, SEAGLAS measure is from 2014, and again, these two are very highly correlated in the cross section, and the results go through with both of them. So that's why we use a snapshot for any type of a risk measure.
Great. So Thomas had there was a couple of questions from Thomas Bodoi-Duramo in the Q&A. So I'll start with the first one. It says, I don't think that mitigating heat stress with milder winters is possible. Indeed, even milder winter can have catastrophic effects, especially in agriculture with early rise of crops, then destroyed by freezing events. We also see a rise in extreme cold events due to chaotic air circulation events from Arctic air. Is this taken into account in some of the estimates in your analysis?
So first of all, any type of agricultural damages are not being measured, taken into account. And that's definitely one of the important channels through which heat and temperatures can cause damages to the economy is agricultural damages. We have few others like damages to infrastructure or healthcare costs, because extreme temperatures tend to cause heat stress for humans as well. Again, these are all components that are not directly captured by our measure, and would probably mean that we are underestimating the total damages. When it comes to these type of extreme winter events, they are implicitly taken into account. Again, we get these projected temperature distributions for different counties. If the extreme cold tail would increase in particular county, that would be accounted for, and the extra heating energy that you would need to spend to mitigate that, for example, for households, that part is captured, and it works against the increased cost during summer, because, or it goes to the same direction. But on average, the winters will become milder. You need less heating energy during winters, and this positive impact is mitigating the negative impact that we have typically during summers.
Great. A couple of questions related to some of the physical climate risk exposure and measures. One says, given Moody's and S&P's analysis on climate physical risk materiality, what would be, in your opinion, a good way to include this risk into a credit rating analysis?
Yeah, that's a good question. It's a question that the agencies themselves are thinking about a lot at the moment. I'm not really sure this is something that is feasible to be done quite yet. I mean, Mike has lots of good work on the model uncertainty when it comes to climate change. The envelope of uncertainty is just so large. There is so much uncertainty what's going to happen, when it's going to happen. I mean, we can come up with some kind of point estimates as we did through SEAGLAS, and we can try to see whether it affects cross-sectionally. But whether those damages are 1% or 2% or 3%, I have very little confidence in separating any of this. And because the credit rating models really are trying to quantitatively capture how close to a default you are, it's very sensitive to these type of assumptions about dollar damages. And because there is so much uncertainty, I think they could very easily just mess up the whole model if you try to incorporate them due to their very sensitive nature to underlying assumptions. So I think what credit rating agents are currently doing, they are acknowledging that these types of risks exist, but they are difficult to incorporate at the moment. But perhaps in the future, as we learn more, they can be incorporated into the analysis. I think that's a very sensible thing for them to do.
Yeah, these are good points. Here's a question, sort of related from Abdullah. He says, does physical climate risk exposure affect the way financial institutions consider lending patterns to developing economies?
This is a good question. So our study only focuses on the US, mainly because of things like data availability. But this is a great question in a sense that, yes, even though there is quite a bit of variation in terms of exposure within the US, you get much more variation between countries, north and south, coastal versus non-coastal. And it oftentimes also tends to be the case that countries that are most exposed, countries like India and Bangladesh, they are also the countries that don't necessarily have the best means to adapt to this type of risk. So you would actually see much bigger spreads in risk exposure between countries than what you see within one country. I haven't seen studies that have looked into this type of things globally in systematic fashion. I think there is some studies looking at sovereign debt across different countries, but like the main challenge with that is that it's a very difficult thing to identify because different countries are so different from so many other reasons as well, that finding a consistent way to capture this would probably be very hard. But my guess is that this is a very important consideration that is taken into account.
Yeah. So we have another question from Diego. He says, it is interesting that you do not find significant effects for other dimensions of physical climate risk. You argue this is driven by the fact that these are smaller and easier to insure. Aren't there weather futures that companies could use to insure against heat risk, or are these markets not broad or deep enough for that?
There exist weather derivatives that you can use to insure against weather patterns up to 1 year in the future. So in short term, yes, you can insure yourself against weather patterns, but you cannot really insure yourself against long-term shifts in average temperatures. That type of market does not exist.
So maybe, we have a few more minutes. So if people have any more questions, put those in the Q&A. I might actually take a chance to ask a question myself here. So the results that you're looking at here, you see these time variation, and they're based on these projected climate damages. I guess what my question is what do you think the right interpretation of these results are? Are these really about people's expectations or the realizations of climate damages? Are these more potentially correlated with their expectations about future policy actions? Sort of what's the right way to interpret these results in your mind, given the time variation and sort of the potential correlation between what these damage measures could mean with other risks associated with climate change?
Yep, that's a good question, and I really don't have a great answer to this. There is like many things that could be going on. So perhaps people have been updating their beliefs about climate change to be more pessimistic over time, started to require risk premium for this type of risk that they didn't require before. This could also be behavioral in nature. Perhaps people are overreacting to news about climate change, although if that was the case, you would probably expect to see some of the other risks load up perhaps more significantly. So I don't have a good answer to that. I feel it's still definitely an open question in the literature that would be very important one to answer. My sense is that given how much model uncertainty there is about this type of stuff, it might be that people are demanding a very high risk premium for this type of a tail risk, which contributes significantly. I also think that it's plausible that there is some behavioral patterns going on. At the same time, I think IPCC's reports have become more pessimistic over time, so also the quantity of risk also probably have increased over time. So I think like all of these components probably contribute, because the effects that we see in some specifications are relatively large and would probably need many different things at the same time to explain them.
I have one more question, maybe a sort of a related question. So how important is it, do you think, that these projections are sort of accurately matching people's outcomes? Like, do we think that people or the marginal investor in the market is sort of in line with these scientific projections? Do you think that really matters? Sort of how important do you think that link is? And do we think that's what is going on?
I think it's important. Let me try to a little bit go in there. So if we look at this 2019 point estimate here, for example, it says that a county that is expected to suffer 1 percentage point losses due to climate change is expected has a spread that is 19 basis points higher than for a county that has no exposure at all. And I think this is actually a very large estimate. And like if you think 1% of GDP damages corresponds to 20 basis point estimate, I think that's too large, which would probably, like, one interpretation of this is that our measure is underestimating the climate damages because we are not accounting for all different channels through which heat affects damages. So if you would, for example, double the projected damages from 1% to 2%, this coefficient would be cut in half. And I think the sensible estimate is probably smaller than what we have here, which would suggest that perhaps we are underestimating the damages.
Gotcha. We probably have time for maybe one, maybe two more questions. Are there any other questions that people have that can either type in the Q&A or that they'd like to ask? I think we're about out of time. So anyways, I personally want to thank Tuomas for his time and for this really great way to kick off our Young Scholar seminar. I think it was a fantastic presentation with some really interesting points to think about. So thank you, first of all, Tuomas, for that. Thank you for everyone who participated in our first webinar. I really appreciate it. We are planning, just to sort of give you a future outlook, we are planning to have these sort of monthly and have these opportunities for young scholars to participate and share their research and present. We hope to have as many of you can come and listen to those in the future, and we'll be sending out reminders and invites for those as well. So thank you so much, Tuomas, and thank you for everyone who participated today.
Thank you so much.